In today's lesson, we're going to move on to a completely new and different topic. Today, we're going to be talking about proof by induction or mathematical induction, and in particular, we're going to be looking at how we prove things using mathematical induction on series. And I do want to remind you that earlier this year, we did already learn about one other style of proof, and that's called direct proof. Today's lesson is about a proof method that's really particularly useful in taking patterns that we notice and showing that they're true not just for the values that we checked and noticed it for, but showing that they're true for all positive integers or all integers beyond a certain value. So we're going to have several days worth of lessons on proof by mathematical induction. There's a lot of different sort of strategies, but they all use the same structure, and today's about that structure. So we're going to need a lot of brain power today, but I want us all to take a deep breath before we get started. All right, now let's do this. So before I actually get into talking about how to do mathematical induction, I want to talk to you about dominoes, right? So imagine stacking up a bunch of dominoes in a row and like knocking the first one over and making them all fall down like in a cool pattern or something. I think that if you want to knock down a long row of dominoes, what you really need to be sure of are two things, right? First, you need to make sure that you can actually knock down the first domino. So, that it's not like glued down or something like that. And second, and just as important, is you need to make sure that all the dominoes were placed in such a way that if any domino fell down, the next one would also for sure fall down. And if both of those things are true, then you can be confident that as soon as you knock over the first one, they'll all fall down, because when you knock over the first one, it'll make the second one fall, and when the second one falls, it'll definitely knock over the third one, and when the third one falls, it'll cause the fourth one to fall. And that's kind of what dominoes are all about. And the reality is that proof by mathematical induction really works in a super similar way. Using this proof method, we're going to show that the thing that we want to prove works in the first case, and then we're going to prove that at any time it works for one case, it'll automatically work for the next one. And by using the principle of induction, it means that it's going to work for everything, right? So it's kind of like what you're doing here is you're checking to make sure that mathematically the first thing that's going to works. And then you show that if I pick any random one in the middle, doing that one will cause the next one to fall over, will cause the next one to work. And if I can show that it works in the beginning and that one of them happening implies that the next one happens, it means that the first one will cause the second one, which will cause the third one, which will cause the fourth one, which will cause the fifth and the sixth, and that process is going to go on toward infinity. That's the idea behind mathematical induction. If you have any questions or concerns about that, I really would encourage you to pause the video and sort of like make a note of those things now and see if they get cleared up through the course of this lesson. If they don't, I really would encourage you to ask me about it. These proofs are more or less guaranteed to show up at least once on the IB exam, and they're really not super difficult to do once you get a handle on the structure. So, make a note of any questions you have, because I really want to make sure that this is clear to everybody. I think that the best way to see mathematical induction and how it works is to just carry out a simple example. So we're going to go through this example, and then I'll sort of take a moment to step back and talk about what all the steps were, and then we'll do a couple more examples, and then we'll be done with this first version of the math induction lesson. So this first example is asking us to prove by mathematical induction that the sum of the first n positive integers is n times n plus 1 over 2. So there are going to be 5 steps in this process, and I'm going to go through all of them right now. So step 1 is that we need to write our conjecture mathematically. And I use the word conjecture here on purpose, because what we're doing is we're supposed to be proving something. And if something we have isn't proven yet, it's a conjecture. It's a pattern that we see. It's something that we've recognized. And so we're going to write that conjecture mathematically. Up here I have it written in English, and I'm going to write it mathematically. So writing this mathematically, it says the sum of the first n positive integers. So that would be like 1 plus 2 plus 3 plus ... all the way up to the first n of them. The sum of the first n, I conjecture, is n times n plus 1 over 2. So what I've done here is I've just written mathematically the thing that I'm looking to prove. Now step 2 is we need to prove what's called the base case. And the base case just means, where are you going to start with this thing? You noticed a pattern. When did your pattern start? Well, our thing says that the sum of the first n positive integers, so in our case, n being 1, so I need to show that this is true for n equals 1. So I want to look at what does the left-hand side of my conjecture say, and what does the right-hand side of my conjecture say, and do they match one another? Well, the left-hand side is where I was supposed to add up the first n positive integers, so that's 1. Okay, so the left-hand side is 1. The right-hand side, according to my conjecture, the right-hand side is supposed to be n times n plus 1 over 2. So that's 1 times 2 over 2. All I'm doing is sort of taking that n value, plugging it into the right-hand side, and when I do that, I get 1. Do you notice that the left-hand side is the same as the right-hand side? Great, so I'm going to write a really brief statement about that. So after showing that the left-hand side was 1 and the right-hand side was 1, I write this little statement like, hey, the left-hand side equals the right-hand side when n equals 1, so the conjecture is true for n equals 1, and we've proven our base case. In the domino example, what we've done here is we've shown, hey, everybody, I'm able to knock over the first domino. It's not glued down, I have enough strength, I knock over the first one. Now what we're going to do is we're going to go on and try and sort of prove that one domino will always knock over the next one. So step 3 in the mathematical induction process is actually a very, 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 very easy step. What you do here is you write out your inductive hypothesis. What we're going to do is we're going to assume that our conjecture is true for some k value. I may not know which one, but I kind of want to take a moment and say, hey, let's pretend that this conjecture is going to work for some particular value of n, and we're going to call it k. In practice, all that means is that we're going to take our conjecture and we're going to rewrite it using k instead of n. So at this point, I'm going to assume that 1 plus 2 plus 3 plus ... plus k, I'm going to assume that that equals k times k plus 1 over 2. Now, step 4 is where the real work happens. Like, step 4 is the hard part of the problem, so we're going to spend some time on that. But before I do that, I really want to make a lot of noise here. Actually, not a lot. I want this to be quick because it's our first example. These first 3 steps are often worth like 3 out of the 7 points of the problem. So even if all you can do is get through this much, it means that you're showing us that you know how mathematical induction starts, and you just kind of fell apart at this last step where we have to prove our inductive step. So even if this is all you can do, that's fine. Practice this much. We're going to get better and better and better at this over time. What we want to do in this 4th step is we want to prove it's called the inductive step. We want to show that the statement is true for the next value of n. We want to show that the statement is true for k plus 1, given that it was true for n equals k. So what I always like to do here is I always like to write something like, we want to show, and then what I'm going to do is I'm going to rewrite step 1 down here, this time using a k plus 1 instead of a k, because this is what I want to show, right? I want to show that 1 plus 2 plus 3 plus ... plus, and this time I don't want to stop at k, I want to add one more number, k plus 1. I want to show that all that is equal to, now the right-hand side with k plus 1 plugged into it. So that would be k plus 1 times, and then if I put in a k plus 1 right here, it would be k plus 1 plus 1. So that's going to be k plus 2 over 2. And at this point, this basically becomes a show problem, right? We are being asked to show this, okay? And huge secret here. Whenever you're doing induction problems, this step right here is going to be the key. You are going to need to use this thing somewhere, okay? So I'm gonna move this stuff up a little bit, and I'm gonna show you how we're gonna go about doing this, and then we'll get to step 5. So I noticed that on the left over here, do you see I have 1 plus 2 plus 3 all the way up to k, right? This is the first k terms, and this is the next one. But we're assuming that the sum of the first k terms is going to be this. So I'm going to replace these first k terms with the thing that I assume that that's going to be equal to. So I'm replacing all that with k times k plus 1 over 2 plus k plus 1. And I'm not going to write equals this because I don't want to be tempted to do things to both sides. This is a show problem. My goal is I'm going to try and do everything I can to this side to make it look just like this side. So structurally, do you see anything that's different between this and this? Maybe you notice that this is all one fraction and this is separate. So maybe I could get a common denominator between these two things. Maybe I could take this thing over here and multiply it by 2 over 2. If I did that, I'd have k times k plus 1 over 2 plus 2k plus 2 over 2. Well, now they've got a common denominator. I suppose I could also have expanded this first thing. K squared plus k plus 2k plus 2, all that over 2. I could even put that stuff together in the numerator. This would be k squared plus 3k plus 2 over 2. Remember, this is a show problem. I know where I'm supposed to try and get to. Hey, wait a minute, I think I could factor the numerator of that. If I factor the numerator, that factors as k plus 1 times k plus 2 over 2. Hey, would you look at that? I managed to show that the left-hand side was equal to the right-hand side. And so just like we always do, I'm going to pause here for a moment. I'm going to write a little statement. When you're doing a proof, you want to write that justification. You want to show all of those. So I wrote here, we have shown that the left-hand side equals the right-hand side. Now the final thing we need to do is we want to write a conclusion. Okay, we've more or less finished our induction proof, and we now just need to write that down. So what I wrote, and what you're going to write for these is often going to look something like this. We showed that the conjecture is true for n equals 1. In other words, we showed our base case. We proved that if it's true for k, it will also be true for n equals k plus 1. So by the principle of mathematical induction, it's true for all integers that are 1 or greater. In other words, sort of in summary, what we did is we showed it worked for 1, and then we showed that if it's going to work for something, it's going to work for the next thing. But proving this means that since it worked for 1, it's going to work for 2. And since it worked for 2, it's got to work for 3. And since it's got to work for 3, it's got to work for 4. Since it's got to work for 4, it's got to work for 5. In other words, on toward infinity, it's going to work for all integers. This is what the principle of mathematical induction and what proof by mathematical induction does and how it works. This first example was long, not because it was a hard example, but because we were trying to talk about what we were doing at each of the steps. What I'm going to do now is I'm going to go over and do a quick recap of the 5 steps, which you really do need to be writing down for all of these problems. These proofs are really a lot about writing and showing your work. And then after that, we'll do 2 more examples, and then we'll finish out the lesson. All right, so the 5 steps in mathematical induction. And remember, you do want to write these things out. You can even write them as step 1, step 2, step 3, step 4, step 5. IB's not going to count it against you if you don't do that, but it really, really helps you to organize your work. Having headings, underlining things, really helps to organize things. So step 1, you need to write your conjecture mathematically. Very often, the problem is going to come to you stated mathematically. So sometimes you don't have to do part 1. But if it's not written as like an equation or an inequality, you got to do that first. Second, you need to prove the base case. In other words, you need to show that the conjecture is true for your smallest n value. Very commonly, that's going to be 1, sometimes it'll be 0, but a thing might ask you, prove that such and such is true for all n greater than or equal to 3. Okay, in your case, your base case is going to be when n is 3. Step 3, you're going to write out your inductive hypothesis. So in this step, you're going to assume and write out what the conjecture is when n equals k. You're assuming it's going to work for some k value. Step 4, which is honestly going to be like the bulk of your work, step 4, you're going to prove the inductive step. In other words, you're going to prove that your conjecture is true for n equals k plus 1 based on it being true for n equals k. It's worth noting that step 4 is always going to use step 3. If you get to the end of an induction proof and you didn't use step 3 for some reason, you did something wrong. Like invariably, you have to use the inductive hypothesis to prove the inductive step. And step 5, the last step, which is still really important, there's always a point in these problems for the conclusion. So if you're not doing this last step, you're definitely missing a point out of 7, and it's an easy point. The last thing you do is you write your conclusion. When you do that, please remember, you need to include the word induction at least. Principle of mathematical induction is better, and you want to include your interval of x values. So is this true for n greater than or equal to 3, n greater than or equal to 1, n greater than or equal to 0? Like, what values is it true for? So these are the 5 steps in mathematical induction. What we're going to do now is we're going to do 2 more examples of this, and so let's get into those. All right. If you feel comfortable and you want to try going through this on your own, I would highly encourage you to try and be a step ahead of me on this. I think it's really, really valuable for you to sort of get a chance to practice these on your own and make mistakes and then sort of see how it works. So if you feel comfortable, try this one on your own and then watch the video and check it along with me. So step one, we need to write the conjecture mathematically. So it says here, prove by mathematical induction that the sum of the first n odd integers is n squared. Okay. So writing the conjecture mathematically. So what I need to do is I need to write out the sum of the first n odd integers, and then I need to write equals n squared. So the first n odd integers, so that would be like 1 plus 3 plus 5 plus ... plus... How would I indicate the nth odd integer? What you'd want to use here is you'd want to use 2n minus 1. Because when I put in 1 for n, that should give me the first thing. 2 times 1 is 2 minus 1 is 1. Cool. 2 times 2, the second one, that would be 4 minus 1, that's 3. 2 times 3, that's 6 minus 1, that's 5. Okay, cool. So this is an expression for the sum of the first n odd integers. I'm conjecturing that this is going to equal n squared. So that's my step one, right? I'm writing this conjecture of what I want to prove, okay? So there it is. Step two, we need to prove the base case. In our case, they said the sum of the first n odd integers. Maybe I should have put positive in here. Our base case is going to start when n is 1, right? So for my base case, I want to show that this is true for n equals 1. So I need to write out what the left-hand side is and what the right-hand side is. Okay. Well, my left-hand side over here on the left-hand side is just the first 1 odd integers, that's 1. And the right-hand side, that's n squared. Well, I only did the first one, so it would be 1 squared. That's 1. Cool. Now remember, I'm going to write my short little statement about what I did here. I mixed it up a tiny bit here. I said, we show that the left-hand side equals the right-hand side, so the conjecture is true for n equals 1, and this provides our base case. Now in step 3, we're supposed to write out our inductive hypothesis. In other words, we're supposed to assume that the conjecture is true for some k value. All right, so if you haven't already done this for yourself, think for a moment, what are we supposed to do in this step? I'm supposed to assume and write down what the conjecture is for n equals k. So remember, all I really need to do here is write this down from step 1 and step 3. So I'm going to assume that 1 plus 3 plus 5 plus ... plus 2k minus 1 equals k squared for some k. All right, so I have my inductive hypothesis. Now step 4, remember this is where the real work comes in. I now need to prove my inductive step. In other words, I need to show that the statement is true for n equals k plus 1. So remember, what I like to do here and what I recommend that you do and what you need to do is you need to write down what we want to show. So we want to show that 1 plus 3 plus 5 plus ... plus 2k minus 1. So this is the sum of the first k odd integers. What would the next odd integer be? The next odd integer would be 2k plus 1. Right? You can basically imagine that what you're doing is you're taking this thing up here, and instead of plugging in k, you're plugging in k plus 1. So when I put in k plus 1, 2 times k plus 1 is 2k plus 2. 2k plus 2 minus 1 is 2k plus 1. I want to show that this equals the right-hand side with k plus 1 plugged into it. That's what I want to show. And remember, and I made a big deal about this on the previous slide as we were talking about the steps, remember that when you're doing this proof, you absolutely have to use this step 3 in there somewhere. So you're looking for an opportunity to use this. So do you see anywhere that you can use this information? Hopefully you notice it kind of shows up in the same place it did before. I can replace all of this stuff with k squared, right? So k squared plus 2k plus 1, that I'm supposed to show that it's equal to this. I'm not going to write equals, all right? So I'm just going to work with this left side. But wait a minute, this is just k squared plus 2k plus 1. I mean, that literally just factors. That factors into k plus 1 times k plus 1, which is k plus 1 squared. This is the right-hand side. I mean, this one was almost easier than the previous one was. Okay, so at this point, we showed that left-hand side was the right-hand side. We're effectively done with our inductive step. I now just need to go on to my conclusion and write out what happened. If you haven't done this on your own, I'd encourage you pause the video and just try and write down your sense of what you think you remember this conclusion to be, and the things that I'm reminding you to mention. Here I went with a very, very similar conclusion to the last one. We've shown that the conjecture is true for n equals 1, and that if it's true for n equals k, then it will be true for n equals k plus 1. So by the principle of mathematical induction, it will be true for all integers n greater than or equal to 1. I'd really recommend that you have this whole thing down. Having all of this down really more or less guarantees that you're going to get the last reasoning point here. You might be able to get away with, by the principle of mathematical induction, it will be true for n greater than or equal to 1, but you're really cutting it close. I think it's worth understanding what the reasoning is that's happening here and being in a place where you can confidently write all of it down. I do have one more example that we're going to go through here, so let's take a look at what that is. So for this final example, I've taken away all the supports. I'm no longer writing what the 5 steps are, and so I want you to sort of practice, get used to writing those steps out. Write down, what are you doing in step 1, what are you doing in step 2, in step 3, in step 4, in step 5. Don't just show the work. I actually want you to write a brief statement about what you're doing in that step. Okay? So here we have this thing. We're being asked to prove that if you do 1 times 3 plus 2 times 4 plus 3 times 5 plus ... on up to n times n plus 2, in other words, a number times the number that's 2 more than that, it will always be n times n plus 1 times 2n plus 7 over 6. I'm not sure how somebody noticed this one the first time, but somebody did. They noticed, hey, this seems to be a pattern that I've noticed. We can prove this using mathematical induction. So again, I would encourage you to pause the video and try working through this, even if you just go through it one step at a time. Think about step 1. Do we need to do step 1? Why not? What is step 2? What is step 3? What's step 4? What's step 5? So step 1 is where I'm supposed to write out what I want to prove mathematically. Well, that's already been done here. So step 1 has really already been done for us, so we're good, right? So my next step, which, I suppose I'm going to call it step 2, step 2 is we want to prove our base case. We want to show that this is true for n equals 1. I felt a little bit weird starting at step 2 and not writing step 1, so I decided to just write step 1, write conjecture mathematically up here to indicate that it's already done. Step 2 is our base case. That's where we're supposed to show that this is true for n equals 1. Now what we did in the past here is we took a moment to write out what would the left-hand side be when n equals 1, and what would the right-hand side be when n equals 1. Right? Well, when n equals 1, it means I'm just doing 1 times 3. So 1 times 3, that's 3. The right-hand side, if I took this and plugged 1 into it, I would get 1 times 2 times 2 times 1 plus 7, that's 9. So 18 divided by 6, 18 divided by 6. Hey, sure enough, that's 3. Right? My left-hand side equaled my right-hand side. And so remember, we write a brief statement about that. So I have something here like, hey, the left-hand side equals the right-hand side, so when n, or left-hand side equals the right-hand side when n equals 1, so our base case is true. Right? Now, what is step 3? Right? For us, step 3 is my inductive hypothesis. Inductive hypothesis. And this is where I assume true for n equals k. Okay? So what I need to do now, remember, is I take my original mathematical statement of the conjecture and I just write it in terms of k. I'm going to assume that for some k, 1 times 3 plus 2 times 4 plus 3 times 5 plus ... plus k times k plus 2, I'm assuming that that's going to be equal to k times k plus 1 times 2k plus 7 over 6. Remember, these first 3 steps really don't require a lot of hard work. They're a really, really quick and easy way to get 3 points out of the 7 that's often given for these mathematical induction problems. Now we get to the real substance of the problem, right? I move on to step 4. Okay. Notice in my organization here, I'm structuring this so that I'm always writing step 2, colon, and then a statement about what I'm doing. Step 3, colon, statement of what I'm doing. Step 4, colon, statement of what I'm doing. I'm really trying to structure this so that the person that's reading this and grading this and understanding it can understand what I'm trying to do. So in step 4, I now want to do my inductive step. My inductive step. And this is where I want to prove that it will be true for an n equals k plus 1. In other words, I want to show that if it was true for this one, it will be true for the next one. Right? So here I want to show that my original statement with k plus 1 plugged into it would be true. So what I tend to do is okay, this thing started out 1 times 3 plus 2 times 4 plus 3 times 5 plus ... I like to write out what the kth term is so that I can see it, and then I write down what the next one is, right? My next one I would get by plugging in k plus 1 to these things. When I plug in k plus 1, I'm going to get k plus 1 times k plus 1 plus 2, that would be k plus 3. That would equal, now I need to write down this thing with a k plus 1 plugged into it. So that n on the top is k plus 1. The n plus 1 on the top is k plus 2. And then this last one, if you haven't already done this yourself, I'd encourage you, pause the video for a moment. If I plugged in k plus 1 to that, what would it become? I'd have 2 times parentheses k plus 1. So that's 2k plus 2 plus 7. So that's going to wind up being 2k plus 9 all over 6. That's what I want to show. Okay? These problems can be really, really intimidating. And this one in particular just looks really scary. But the thing I want to remind you is you are always, always, always going to use step 3. This thing is going to come in somehow to save the day. So I'm going to try and use it right now. I notice that the left-hand side, by the way, if you haven't tried this on your own, it's like pause the video, see if you can see even what the next step is, and see if you can follow it somewhere. This stuff right here is this stuff, which means I can replace it with the other side of my inductive hypothesis. Okay, so I'm going to replace this with k times k plus 1 times 2k plus 7 all over 6. That plus k plus 1 times k plus 3, that's the thing that I'm going to try and show is this. And that's probably going to take some work, but that's okay. We can do it, right? What do I notice that's structurally different between these two things? Well, again, I notice that this thing is all one fraction, and this is over 6, but this stuff isn't over 6. So I'm thinking that what I do here is I take this and I multiply the top and the bottom of it by 6, right? When I do that, I can put these two things together. So on this one, I have k times k plus 1 times 2k plus 7. This is all going to be over 6. And on this one over here, I have 6 times k plus 1 times k plus 3. Now remember, we're not in the dark here. We know where we're trying to get. We're trying to get to this, right? So look at what you already have going for you. What I already have going for me is this already has a 6 in the denominator. Then there's supposed to be factors of k plus 1, k plus 2, and 2k plus 9. I can think of 2 ways to go about working through this, okay? One of them is to just superfoil this whole thing out and combine it and then factor it down to this. The other is to be a little bit smarter. Do you guys see a common factor between this and this? Do you notice that both of these things have a factor of k plus 1? If I factored out a k plus 1 from this first thing, what would be left? Wouldn't it just be k times 2k plus 7? Right? And if I factored the k plus 1 out of this, I'd be left with 6 times k plus 3 all over 6. Right? Now, I don't want to scroll down too far because I don't want to lose sight of what I'm trying to prove up there in the corner, right? This is what I'm going for up here. So I'm going to simplify what's inside of here. This is, I've got k plus 1 times these two things multiplied together give me 2k squared plus 7k. These two things together give me 6k plus 18, right? And this is all over 6. I could combine these two things here to give me 13k. And so what I really have on the top here is I have 2k squared plus 13k plus 18. But I think you'll find that, coincidentally, k plus 2 times 2k plus 9 will multiply together to give me that. In other words, the numerator of this thing is k plus 1 times, k plus 2 times 2k plus 9, and this is all over 6. This thing is literally what we wanted to show that it was. At this point, we've proven our inductive hypothesis. We prove that starting with the knowledge of this being true for n equals k, it's going to be true for n equals k plus 1, and so all I need to do is write my conclusion. I know that this video has gone long. It's been a little bit longer than I wanted it to be, but let's finish out this conclusion strong. And that's it. We finished our third example of mathematical induction. Certainly for the rest of this week, we're just going to be doing more mathematical induction. I will be extending it into other kinds of problems, but the steps, those 5 steps that we did, are always going to be the same 5 steps. By the way, I just realized I forgot to write here that this is step 5, conclusion. Okay? So if you have any questions about this, I really hope that you wrote them down and that you'll ask me about it. Mathematical induction is really hard to get your head wrapped around at first, but once you get the hang of it and you've practiced a few of them, it really gets to be pretty straightforward and actually fairly quick. So best of luck as you work through the exercises on these, and let me know if you've got questions.